Welcome to this video. In this video we will be discussing regarding some notations and the Lie groups and Lie algebra properties. So we have been discussing regarding this SL2C group and how it is related to this Lorenz group. But we saw that there were two elements of SL2C which mapped to a single element of the Lorenz group. But while discussing the Lorenz group, we didn't completely specify that this Lorenz group is it is actually a part of the the actual Lorenz group is defined in a different way, and the Lorenz group that we were talking about was a subset of it. It was a subgroup. So we will first discuss that part, and then we will also discuss a bit of regarding this Lie algebra and the Lie group properties. It won't be a detailed discussion, and it will be just scratching the surface. So let's see. So in general, Lorenz group is any group that will preserve this quadratic form that I have written here. This is just the Minkowski dot product of the four vectors, and the group elements of this Lorenz group will satisfy such a relation where this is the metric, the 1 minus 1 minus 1 minus 1, that is the signature we are using. But this Lorenz group that SL2C forms a double cover is a bit different, because you see it is actually a subgroup of this Lorenz group, of the Lorenz group. So because to get this point, we see that if this is satisfied by every group element, then we can put alpha and beta equal to 0 and get this relation, and then this we can explicitly mention these summations that will give us this second line, and that means this 0 component of any Lorenz group element, this lambda mu nu is a Lorenz group element, its 0 component will be the component square will always be greater than equal to 1. Now this can mean two things. One can be that the component is greater than 1, or it is less than minus 1. So now which one will be for this Lorenz group, that is the double, that SL2C forms a double cover, we take the first one. So these the particular group elements of SO3 plus 1, 3 are those elements which have the 0 component as greater than equal to 1, and they are called orthochronous Lorenz group. Similarly, one more property we will or the constraint we will give, that is coming from this determinant part. So lambda transpose G lambda is G, that is just the matrix form of this equation here. So once we have that, we can say that the determinant square is 1, because the determinant AB is determinant A times determinant B. So now what we can do is, we see that the determinant can be plus 1 or minus 1, but we will only work in this condition. So with these two constraints, this is the constraint saying it is proper, and this is orthochronous. So it is a proper orthochronous Lorenz group that we are working in, and the name is SO plus 1, 3. So why we will be working in this group? One of the reason is that this is the group we will see while discussing about this Lie groups. This is a group that is continuously connected to the identity element. So that we will see now. So we look into some aspects of Lie groups. Now what are Lie groups is that in very simple terms we can say the group elements of Lie groups, they are continuous differentiable functions of certain parameters. So you have a set of parameters, it can be like r, theta, phi, and the parameters, they lie in suppose some subset of R3 or in general some Rn. They can be complex also, then it will be Cn, and this is a space of parameters. And if the elements of a group can be written as differentiable functions of these parameters, we say that the group is Lie group. So in this notion, the parameters can be chosen freely, they can be adjusted so as the G of 0, that means all parameters are set 0, is identity. So with this small notation, we fix the identity element, which is G of 0. Then we can Taylor expand any group element, because they are differentiable functions, about this identity. And then once we do that, what we will get is, suppose you have a group element that has various parameters and characterized. So like, it's actually, suppose there is a group element, it is a parameter of theta, phi, gamma, like this, that I am collectively calling it as theta A. So this can be written as, you first write G at 0, that means all parameters set to 0, plus now you will Taylor expand it, so there will be the derivative of G times derivative evaluated at 0 times there will be this coefficients. So that coefficients then can be they can be completely arranged in this exponential form, because you see, if I exponentiate this, if I Taylor expand the exponentiation, then it will be 1 plus I theta A Ta, where this means it is summed over, and then you have the other terms. But the second term is actually the derivative, because it is the Taylor expansion of this side. So that gives us this criteria for determining the TAs from the group elements. So this TA is called the generator, and you can see that because these real parameters, they can be complex also, because these parameters, they are not like well defined. They can be like a linear combination of this parameter will also give a new parameter. This means that this TA that we have here, this TA, there can be linear combinations of TA, which also gives us the new generator. So this means that there is a exact proof of this, but the point is this TA, which are the generators, they form a vector space. So once we have the group element characterized as this exponentials of the generators, that's why they are called generators, because you can exponentiate the generator to get the group element. The next thing we can ask for is how we can ensure the group composition. So the group composition means that you take two exponents like G of theta A and theta B, and you know how to product them. But this is quite easy, because we know that using the Baker-Campbell-Hausdorff lemma, what we can show that this is like this. I have proved this in one of my videos. So once we prove this, then we can now say that if this has the factors of theta and t, and this also has theta and t, the commutators of different kind of generators that are generating. So you see, if you have three parameters, because there is a summation, you will have three generator in your space. So these different generators will enter in this commutation relation, and so to understand the group composition, we need the commutation relation of the generators. The commutation relation of the generators of a Lie group, they are what we call that, we call them as the algebra of that group. So this is the algebra associated with a Lie group that I have shown here. So this is the algebra that we say that is associated to the Lie group. So here these are the generators, and there is a sum running over C index here, and F, A, B, C are called structure constants. And if the parameters can be chosen to be real, if we choose the parameters to be real, all the parameters, then all the structure constants will be real. So that is what we will do in most of the cases, because the parameters will represent something that is real. We will see later. So with this we come to an example. So the example is simple. It is just the example of the Lorenz group. So you see, Lorenz group is a group that, suppose it keeps this kind of a dot product, Minkowski dot product invariant. But now how we know that this is a matrix representation? The point is to every so this matrix, it represents the boost of the Lorenz group. So why this matrix represents the boost? Because this is what we call as a representation of Lorenz group. Like, this is one of the representation. In general, given a group element, a representation is a map that takes the group element into some linear operator that can be defined on a different vector space. So representations in a very simple way extends the group's action into two other vectors. Like here we can act it over a 4 vector, precisely because we have a 4 vector representation here. So this is what we mean by representation of Lorenz group. Now this is a group element. It is the representation of a group element. The element is the boost, and to get the generator of the boost, what we do is we simply differentiate it with respect to the parameter that we have. So here we have the rapidity as the parameter. So what we can do is we will just differentiate with respect to phi and put phi equal to 0 to evaluate the generator. So in this way we get the generator of Lorenz group, but this is just corresponding to one of the boost along the x-axis. Similarly, we have rotations. This is a rotation. So here this 0 that I have written here, it is 2 cross 2. This is 2 cross 2. This is identity also 2 cross 2. Here also it is 2 cross 2. All of them are 2 cross 2 because it is a 4 cross 4 matrix. So this is a rotation about x-axis. So again we perform the same differentiation to get the generators. In the similar fashion, we can perform the differentiations of other boost elements. So there are 3 boost, 3 rotation matrices. So we will get 6 generators because we have 6 parameters. So the parameters of Lorenz group are this rotation by an angle theta. There can be 3, and boost along 3 different directions. That is 3 parameters for rapidity. So with this understanding, we have 6 generators that I have written here. And the point is, these generators can now be combined in a very simple manner, because it is always difficult to write this entire matrix form. What we can do is we introduce something called as a anti-symmetric matrix notation. So we say that this is equal to some T01, this is equal to T02, this is equal to T03, and this is equal to T12, this is T13, and this is T23. And with these 6 things, we can now we can arrange them like this, where this mu nu is the muth row and nuth column, and this lambda row is this anti-symmetric index. It is anti-symmetric in the sense that T32 will be minus T23, and T33, T22, all these terms are 0. So we will see why this is important, but for now let's move forward. So we have understood this matrix notation, and we have seen explicit form of this Lorenz group element. But the point is, we also have the algebra of the group, because once you have this, suppose this representation in 4 vector form, it's not hard to compute these various commutators, and this is the representation of the group written explicitly. So this representation of the group, this is the algebra of the group, and this algebra of the group we can derive it in this 4 vector representation, but the point is it will be valid for every representation. So algebra of a group is representation independent. So with this we have this is the algebra. One thing that is important to see is that the rotation generators, that is this J's, they itself form a subgroup of this SO3 plus, SO3, 1 plus, or this proper orthochronous Lorenz group. How we can see that is that if we look at this particular algebra, this is SO3 algebra, and we see that, so we have the SO3 algebra within, it is contained within the this SO3, 1 plus. But you see, you also have the boost, but the boost algebra is not self-contained. That means two commutators, the commutators of boost is not another boost, it is actually a rotation. So this is an important thing to remember, and with this understanding we further move to see why the notation of this form, this T lambda rho mu nu, why does this work? So the point is, any Lorenz group element, it can be written in this form, and you can expand it around the identity. So this is the identity element, this is like the second order expansion of the identity. So you will have higher terms which will be order omega square, but this omega, it is constructed of the boost parameters, rotation parameters, and their corresponding generators. There is a sum over this A, but this is a group element, so this must satisfy this particular property here, the Lorenz group property. But we will just plug this delta up to the first order expansion, we can plug it here, and once we plug it, we see it of this form, and the final thing that we will get will have this omega square, but as we are expanding in small order, we will neglect this, and finally we will see that this omega is anti-symmetric. This anti-symmetric omega is the first order expansion of a Lorenz element, a Lorenz group element, and this anti-symmetric omega can be written in particularly this form that we were discussing. These are the J and K's, and these are the parameters, boost and rotation. And then from here to here, what we have done is we have made use of the symmetric index notation. You see, I said that this T is the T is anti-symmetric in these two indices. This omega are the boost parameters. These are also anti-symmetric. They are parameters. And then I have introduced a half factor here, so that I can run over all the rows and sigmas, but then if that happens, then we will be doing double counting, because the parameters are anti-symmetric. So with this, the final group element is this particular thing here. So this is the representation of Lorenz group, and it acts on the spacetime vectors or the 4 vectors. So now we have understood a bit about this Lorenz group and their actions. Let's further try to see in a bit more detail what this algebra, this Lie algebra that we saw here, what this algebra is telling us. So the algebra, if we arrange the boost and rotation matrices, so in this particular representation we have this matrices, and if we arrange them in this particular fashion, we see that the Lorenz group algebra, it actually decomposes into two SU2 algebras. So because you see, this is one SU2 element, this is another SU2 element, because precisely this is an SU2 algebra property, this is also an SU2 algebra property. And further, there is a direct product because they commute with each other. The point is, this can be an SO3 algebra also, but SO3 algebra and SU2 algebras, so SO3 and SU2 in algebra level, not in group level, in algebra level they are same. So but once we have this kind of relation, we can connect it with something that we know. So if we remember, so what we have on this left hand side is that, suppose generator of rotation, so this particular connection that we have, and along with these particular elements, if we add these two, we will get a generator of rotation. So what we are saying is that rotation generator is the sum of two generators of SU2 algebras, but SU2 algebras are the poly algebras. So it is, this particular equation is like saying it like, and rotation generators, if we remember, they are like the angular momentums, they generate rotation. So we can say that this is like a total angular momentum, which is the sum of two spin angular momentum. So this is simply the vector summation of spin angular momentums. So with this understanding, we a bit of understanding from quantum mechanics, we can also see that suppose we take spin half particles, because SU2 they represent spin half. So if we take spin half particle, so we know that if two spin half particles are there, we can add them. So the J value, that is total angular momenta, it varies from J1 plus J2 to mod of J1 minus J2. So you get a singlet and a triplet. This is a triplet because there is the MJ values, that is the projection along the Z axis is -1, 0, 1, and this only has 0. And the point is precisely that if we look at the JZ, so we had here JZ operator, this is a matrix. If we try to diagonalize this matrix, so the diagonal values of the matrix are like this MJs. So these values will actually give us 0, -1, 0, 1. So this is further showing that why this particular J operator, it is the sum of two spin half particles. And in a more precise sense, what we can say is that this representation that we saw here, it is a representation of two spin half particles. So this is a notation of this representation. We can represent this representation of Lorenz group is called half-half representation. Now if we want just a single spin half representation, we can say that we will put one of the j among j plus and j minus to be 0. So which j will be put to 0 is actually creating a difference now. So the point is, if we have spin half particle, we are not sure about which j to put 0. So suppose you have this suppose j plus is put to 0. In this equation, if we put j plus 0, then you will get ji equal to minus I ki. And further this j minus, if this is 0, then this is just remaining, and because this is an SU2 element, SU2 algebra element, we can write this particular thing. So this equation is showing us that if we have a spin half particle Lorenz representation, then the rotation generators are sigma I by 2, and the boost generator is iota sigma I by 2, where sigma are the Pauli matrices. Further, you can also try to put the this plus one as half and the other one as 0. But once you do that, you will see that this is a different representation. So the point is, based on which of the spin component is put to 0, the representations are actually not the same. And this is what we saw in the previous video, that there were two representations, two types of spinner, left-handed and right-handed, and they transformed in a bit different way. And what was the difference? It was precisely that the rotation transformations were the same, sigma I by 2, but the boost transformation were transforming with a minus sign. So with this we understand that in reality the Lorenz group, it can be split, this proper orthogonal Lorenz group, it can be split into a direct product of two SU2 groups, and these SU2 groups, they, because of such a distinction, we are getting these two spinners which are left-handed and right-handed. And the Dirac equation is in some sense a relation that relates the left-handed spinner with the right-handed. So that's all for this video. What I wanted to convey was that the left-handedness and right-handedness in Lorenz group is actually a consequence of the underlying algebra, and which is very fundamental to the group. So that's all.